All right, welcome everybody. It's great to see this excellent turnout. We are delighted to have Robert Huang as our speaker today. Robert wrote a truly pioneering PhD thesis on quantum shadow tomography, and then more broadly, learning from quantum systems. And then he's continued to develop that program as a postdoc, and will be starting in a month as a professor at Caltech. And so he's here for a month, actually, sitting on the third floor of Varian. And so if you are interested in what he's saying, don't be shy about going to knock on his door and chatting with him. And Robert.
Yeah, thank you, Patrick, for the introduction. I'm very happy to be back at Stanford. And today I'm going to talk about quantum advantage in learning and sensing. And this is going to be more of an overview talk. I would talk about I will review some of our earlier developments, as well as some of our more recent findings. So as scientists, we all know that the central goal of science is to learn how our universe operates, from the microscopic levels, like understanding atoms, how to control them, to understanding astronomical objects like black holes, planets, stars, etc. And by developing our learning tools, it can help us design better catalysts, design better pharmaceutics, gain new understanding into exotic quantum matter, and build powerful quantum devices. So since learning is going to play a central role of my talk, I would like to start out by talking about what I mean by learning, just to kind of set the stage. So first, there's going to be some external world that we would like to learn about. It could be some properties of quantum systems. It could be some signals coming from outer space, etc. And I'm going to consider that we have some advanced intelligent agent that represents us or a future machine if we're no longer here. But these AI model agents, they can try to their goal is to try to learn and control the external world. So what it could do is it can specify certain inputs that will affect the external world and utilize all kinds of, say, sensors or microscopes or etc. to retrieve information from the external world. And it can then process these information obtained from the external world to start to form a mental model of how the external world looks like. So via these interactions, it can slowly build up some model about our world. And at the end, it will have this model formed. So this model can really mean all kinds of things. It could be some properties of a quantum system that the AI agent is trying to create in the lab. It could also be the phase diagram of a material. It could also be some properties of a dynamics. For example, I'll talk about whether dynamics satisfy time reversal symmetry, etc. It could also just be some parameters that we would like to sense about our external field that's coming in, let's say, from black holes far away. So that's the definition of learning that I'm going to be working with. So it's a very broad definition. And there are two common ways that we can divide between these AI agents. So over the past several years, we have developed this notion called classical AI agent, or just classical agents, versus quantum AI agents, or quantum agents. And I just like to briefly review them. So classical agents, they can interact with the external world classically. So it can receive classical information from the external world by performing measurements, by performing experiments. And it can then process these classical information using classical computation and storing these classical information in classical memory to form its mental model about our world. On the other hand, as quantum technologies start to develop, we can utilize the entire suite of quantum technology to develop something that we refer to as a quantum AI agent, which can learn about the world quantumly. So it can receive, process, and store quantum information about the external world. So for example, it can utilize quantum sensors to extract quantum information signals from the external world, use quantum transducer to transduce that signal into its quantum computer. It can then process these quantum data using quantum computation, storing them in quantum memory, And the hope is that using these more advanced quantum technology, quantum AI agent will be able to learn better, make more accurate predictions, and discover things that classical AI agents would not be able to discover. And hence, one of the overarching questions in this research program is the following. How can quantum AI agents obtain meaningful and hopefully useful advantage in learning about our physical world? So this is the main question that I'm going to talk about throughout this talk. I'm going to do some brief review and then talk about some of the latest development. So the outline of the talk is as follows. First, I would review some of the power of quantum agent, rigorous mathematical proofs that we have established over the past several years in understanding where we can get exponential quantum advantage in using these AI agents. And then I'm going to talk about some of the surprising limitations that we have found over the past year. That is in connection to some of the developments that's also happening here in random unitaries. Going to utilize these tools to talk about limitations of advantages or things that quantum AI just cannot learn. And then I'm going to switch gears and start talking about sensing. So a lot of the topic in the first part of my talk will be about learning quantum systems, about learning quantum many-body systems, where the learning task is inherently quantum mechanical. And hence, even though it's nice that we can get quantum advantage, very large one there, it limits some of its applicability to real-world applications. Now, in the second part of the talk, I would like to start moving closer to more classical learning problems, in particular sensing classical fields, and talk about what kind of advantages that we have discovered very recently. So diving into one of the paper that was done by me, Huang, Chan, and other people at MIT Harvard. So let me begin with the first part on power of quantum AI. So over the past several years, we, together with many of my great collaborators, Richard Kuhn, John Pascal, Sit-Han Chen, Jordan Cutler, Jerry Lee, and many others, we have established large quantum advantage in various different quantum learning problems. So I'd like to just provide a brief review of the theorems that we established there, what are the problems look like, and what kind of advantage can we get out of it. So one of the first tasks that we looked at, which is inspired by shadow tomography, is in predicting observables. So here the goal of the AI agent is to try to learn a model about an unknown n-qubit state rho, such that after learning a model, it can utilize this model to accurately predict the excitation value of all the Pauli observables coming from this set here. And one of the first results that we established was that we can prove that any classical AI agent that can perform measurements on the state rho in each experiment to obtain classical data, it can process it classically and select the next experiments that we do. One can prove that the classical agents will require an exponential amount of experiments in order to solve this task, whereas the quantum agent can only requires a linear number of experiments to predict all of these Pauli observables. So this provides one of our first tasks where we can see an exponential separation. But there are also various others using a mathematical framework that we have developed several years ago, a few years back, where we, another example is in relation to a task known as quantum principal component analysis. So here we still have an unknown n-qubit state in the lab, and we wanted to estimate properties, we wanted to learn properties of its principal component. So the principal component is just the largest eigenvector corresponding to a given quantum state rho. And let's say we wanted to learn some fixed property like Z1. We wanted to measure the Z operator on the first qubit of the principal component. So this is a task known as quantum PCA. And previously, there's already quantum algorithms that were achieved for doing quantum principal component analysis by Sassoy, Masu Masani, and Patrick Raventras. However, only in the past few years, we were able to show that for this task, there is actually also an exponential advantage because we can prove that for any classical AI agent, it will require an exponential amount of time to learn this property, whereas the quantum agent only requires a constant amount of time under the assumption that there's a spectral gap. So the largest and the second largest eigenvector has an eigenvalue that's gapped by a constant. So this is just another example where we can establish an exponential advantage in learning about physical systems.
In your previous example,
Yes.
Do you know P in advance, like when
No.
the experiments?
No. So in this case, one can consider the following setting. So the quantum agent is required to be able to predict all of them, in the sense that someone could come to the agent and keep asking different Pauli observable, and the quantum agent just needs to keep answering it basically. And the classical agent doesn't know what P is, and just and will be given one after it learns the model. So otherwise, if it already know P, then the classical agent can just measure the Pauli observable and get the answer. So here, it's important that the Pauli observable is not known in advance.
Why are you calling your agent artificial intelligence?
Oh, sorry. It was clarified a bit earlier. It's advanced intelligence. No.
Oh.
It also includes like humans and. But yeah, and another examples of quantum advantage that was identified in our earlier works is the following. It's about learning and properties of an unknown unitary. So in this setting, we can imagine that in the physical world, there's some unknown physical process that's just happening there. And let's say it's an n-qubit unitary dynamics. And the AI agent is trying to decide whether this unitary satisfies time reversal symmetry or not. So it basically just means whether that unitary is all real number, or it has some imaginary part. And for this task, we can also show similar exponential separation that a classical agent, so what can a classical agent do? It can prepare an arbitrary state, evolve under the unitary, and then just measure it to obtain classical data from each experiment, process them classically, and select the next experiment, and doing it iteratively. Such an agent would require an exponential amount of time in order to uncover whether the unknown unitary has time reversal symmetry or not. On the other hand, the quantum agent only requires a constant amount of time to distinguish between the two cases. Basically, the quantum agent would utilize its quantum sensor to extract the alpha state, put it into its quantum memory, and then create some entangled state and do a second experiment. And then again, utilize quantum sensor, take the quantum state back, and then do a little bit of processing on its quantum computer, and then it will be able to uncover this symmetry. So these are just a few examples that we have established. And over the past 3 years, people have also identified exponential quantum advantages in learning quantum noise, which has a very nice experiments done by the IBM team. People have also established quantum advantage in learning about continuous variable systems like bosonic displacement channel. And we have a recent paper together with Liang Zhang and also Ulrich in Denmark that establishes that, which I believe Ulrich has given a talk in this QFarm seminar some weeks ago. Yeah.
What's the state? What's the requirement or condition on the state preparations?
So here quantum agent can do whatever it wants to do. So it can prepare, say, like a valid state, or it can prepare some arbitrary entangled state. On the other hand, the classical agent, we can show this even when it can prepare arbitrary state. So it can produce arbitrary quantum state, evolve under the unitary U, and then perform arbitrary measurements, arbitrary POVM. And so that constitutes one experiment. And then we can show that a classical agent will require an exponential number of experiments in order to tell them apart, to tell these two cases apart. Whereas for the quantum agent, what it can do is it can essentially prepare a bell pair, like a bell state, and then apply U on one end. And I remember doing some operations and then apply U again, and then do some entangled measurements. And the data that comes out of it would allow it to distinguish between T symmetry versus not. That's the setup in this case.
But the quantum agent doesn't have the ability to like that.
Yes, so here we're always assuming that all of them can only apply forward time evolution. So yeah, so over the past few years, we have seen these advantages, which raises hope that quantum AI agent can really be powerful. However, there are also some tasks that people are excited about and look quite simple, And yet we don't seem to be able to find efficient algorithm like quantum AI agent to solve them or to get quantum advantage out of it. And over the past year, essentially, along with people here, we have developed techniques that allows us to answer some of these questions. So what I would like to talk about in this next part is the limitations on quantum AI agent. So there are some tasks that seem simple and that seem very quantum mechanical, and yet there cannot be any quantum advantage that exists. So one of the tasks is the following. So we want to tell time. So what is the precise setting? The precise setting is there's some unknown unitary U, which is guaranteed to either be some 1D short time dynamics. So it's some unknown dynamics happen in nature. It's either 1D short time dynamics or it's some 1D exponential time dynamics. So think of that 1D exponential time dynamics to be generic, to be hot random, and so on. And the question is the following. Can there be some large quantum advantage in distinguishing between short time versus exponential time dynamics? So the AI agent is able to access this unitary by evolving under it. It can prepare some initial state, evolve under it, and then retrieve it. So classical agent can only input and retrieve classical information, but a quantum AI agent can put in some input state that is entangled with itself and retrieve the output state completely coherently and do further processing. And we can ask this question. So we can specialize this into two specific setups. The first, we can ask the question for, let's say, classical dynamics and look at what happened. And then we can ask the same question for quantum dynamics. Let's say we look at the case for classical dynamics. So the unknown unitary is just an unknown classical process. So one could think of it as a reversible classical circuit. So there's only classical dynamics. Then in this case, it's actually not hard to show the following result that says both classical and quantum AI agent can efficiently tell apart between short time versus exponential time 1D classical dynamics because this task is very easy. It's in a way too easy to host any quantum advantage. So what happens here? Basically, or what is the algorithm to do it? Essentially, the classical AI agent can just do the following. Just inputs either the two states, the all 0 bit string, and also another bit string, which is 1, and then everything else is 0. Now you can look at the output state, output classical state that comes out of the classical dynamics. And the case when the time is short, like short time classical dynamics, then this difference in the first bit will cause, due to light cone effect, will only cause the first few bits to differ. So if you look at the output, the first few will be different when the dynamics is short time. But when you have an exponentially long time dynamics that is generic and random, then basically all of the bits, like the difference will happen everywhere. And hence, just by checking what are the bits that are the same and what are the bits that are different, one can efficiently tell apart between short time versus long time classical dynamics, just by testing causality. So there's no advantage in this case because in a way, this is too easy. However, one could ask the same question. What about for quantum mechanical, quantum dynamics? Some quantum many-body dynamics, it's an unknown quantum unitary. Can there also be a large quantum advantage in distinguishing between short time versus exponential time dynamics? One might have thought that, oh, maybe there should be, or maybe not. But what we found was that somehow by changing classical dynamics to quantum, then suddenly it becomes extremely hard. Then we can prove that no classical and quantum AI agent can efficiently tell apart between a short time 1D dynamics from an exponential time 1D quantum dynamics. And as a result, this is too hard for both classical and quantum, and hence again, there's no quantum advantage in this. So in order to establish it, so this is quite a surprising result that we found in the past year. And there are two papers that need to be combined in order to establish this. The first is with Fermi Ma on how to construct random unitaries, where we provide the first construction of pseudo-random unitaries under standard cryptographic conjecture. The pseudo-random unitaries are basically just unitary dynamics that is indistinguishable from these exponential times, but then themselves are polynomial time. And then in the second paper, with Tommy Schuster and Jonas Tafferkamp on random unitaries in extremely low depths, we were able to compress these PRUs into very short time, and essentially this result comes out. So this sets a limitation on this very simple looking task. that says, oh, I'm just trying to distinguish between short versus exponential time 1D dynamics. And this is hard for both classical and quantum AI agents. So something that comes into this is that basically in the classical world, we need at least linear time to behave random due to the light cone argument. However, in the quantum case, somehow we can scramble exponentially faster, and just with a short time, it would already look like an exponential time dynamics. And together, it tells us that quantum AI agents are not that powerful. It does have a lot of advantages in uncovering symmetry, in predicting observables, and so on. But yet, we cannot tell time. We cannot tell between short time versus exponential. So there can also not be any large quantum advantage here because the task is hard for quantum AI agents. One could also look at another task, which is of more interest to many people studying topological order. So the task of classifying topological order. There have also been this discussion about whether there could be quantum advantage if we.
So like, I mean, this chaotic dynamics, I guess you have like some statement, you made some statement about some chaotic dynamics.
So yeah, so in a way, here the statement is that there exists some short time super chaotic, like very chaotic quantum dynamics such that this holds.
Mm-hmm.
And our belief is that, or the current belief that people have right now is that any random quantum circuit that is shallow should also have this phenomenon.
But if the quantum circuit is not chaotic and it's not optimized and instead some well-defined path which is not chaotic, like can you then say that there will be some difference, or is it just too hard to specify what exactly the process is?
That's actually a good question. So here, this is more like a generic statement about generate chaotic quantum dynamics. But if there's more structure that you place in, then I think there will be cases where there could still be advantages that can happen. Like maybe there are certain patterns inside the dynamics that only quantum AI agent can tell. So somehow, like for example, one can try to, and then try to embed things, and then one could tell. So this is more about generic quantum dynamics. So another task that people have studied a lot is in classifying topological order. Just a brief recap. So when we have some geometrically local shallow circuits, it will not be able to alter long-range entanglement. So for example, if we have product states, then there's no range entanglement, and hence after applying shallow 2D circuit, it will still have no long-range entanglement. On the other hand, if you have something like torcogram state, which has long-range entanglement, and now after applying shallow 2D circuit, it will still have no range entanglement. And hence people have this notion of topological order, which are essentially equivalent classes. That says if two states have the same, like the state side, if two states have the same topological order, it means that they have the same long range entanglement structure, vice versa. And hence one can define these two families of states. One consists of product state perturbed by shallow 2D circuit, which are known as the trivial order, versus the topological order, which are the collection of states created by applying shallow 2D circuit to torcogram state. And over the past few years, there have been works that try to utilize, for example, some quantum neural network to showcase maybe there's efficient way of classifying between these two cases, and with the hope that maybe there's quantum advantage in doing so. And hence it raises this question, given copies of a state psi that is either from this family or from that family, is there a large quantum advantage? The goal is to classify if the state psi is topologically ordered or not. So there have been a lot of more empirical works. Seung-Won Choi also has some works on using QCNN to try to do this. However, most of these are purely empirical, and hence it's not yet clear what the answer to this is. So just to kind of recap on what people already know. So there have been several works that combined together, one can easily show that if we have a classical AI agent that try to classify, want to train them to classify topological order, they can always do it in a computational time that's exponential in correlation. So basically what one can do is one can train these AI models and then try to make it learn and say test for these minimized topological entanglement entropy, which gives a good signature for classifying the two cases. And however, these methods has this exponential scaling in correlation length. which means when the correlation length is slightly larger, like a few hundred, then suddenly all of these classical AI agents will be highly inefficient, and in practice will not be able to classify between these two cases accurately. However, there has been hope that maybe if I train some quantum neural networks, some quantum AI agents, it will be able to efficiently classify between them. However, what we were able to prove, essentially using a similar strategy, that short time is indistinguishable from long time, one can show that even for the most powerful quantum superintelligence of the future, in time that's complex exponential in correlation length, random, trivial, and topological order states would both look called random, and hence it would also not be able to distinguish them. And together, these statements essentially establish the following result. Some version of the theorem is also in the paper Random Unitaries in Extremely Low Depths, where we showed that under standard cryptographic conjecture, there are also no large quantum advantage in classifying topological order. Because either when the correlation length is short, then classical AI agent can also do it efficiently. And on the other hand, when the correlation length is large, then both classical and quantum AI agent just fail.
Does this hold even if you're in a setting in which you just have two Hamiltonians and you want to talk about the ground states, or were you just talking about states that are constructed from circuits?
Yeah, so here, this is more, so these states also have polylog local Hamiltonians. So there are Hamiltonians, but the Hamiltonians are not given. So it's not like these kind of public key setting that Adam Boulon has been studying. So this is just, we're given some copies of states. Let's say the states are generated in the lab. And now I just wanted to do some processing to tell if it's trivial or it's topologically ordered. So there's also no notion of Hamiltonians. So yeah, so far, on the side of understanding quantum advantage in learning, we have large advantages in some quantum learning problems, like the one I talked about earlier. However, over the past year, we've also found that actually for some of these simple looking problems or some of these physically relevant problems, there's also no advantages. So the landscape of quantum advantage is really quite subtle, even though we have all of these. And furthermore, all of these results so far has been focused on advantages in a purely quantum problems. So like learning about quantum states, learning about quantum dynamics, and so on, which limits its applicability. So one of the questions that easily arises is that, can we have large quantum advantage also in some more classical looking problems? And this has there have been a lot of work in quantum machine learning that tried to tackle this, but so far there's mostly been negative results. So there have been a lot of very nice quantum algorithms that were developed. Over many years, people thought there's exponential quantum advantages for classical data analysis, but over the years, people realized, like initiated by Ewan Tan and her collaborator, they figure out that actually there's no quantum advantage in some of these classical data science problems. But I don't think that kills the entire hope. So the hope here is that after we have fully rigorously established these quantum advantage in quantum problems, maybe we can slowly move towards more and more classical problems using some of the rigorous tools that we have developed over the years. So that's what I'm going to talk about in the second half of my talk. In particular, what I'm going to focus on is this task on sensing classical fields. So sensing classical fields is a problem that has wide-ranging applications, from probing materials properties to observing merging black holes, for example, by detecting the space-time fluctuation that is coming through Earth, to problems such as detecting dark matter. And also there are tons of other ones, for example, in brain imaging or potentially even in some classical technology like self-driving cars, maybe we can make even better sensors, etc. So quantum sensing has also been a very broad field with a lot of activities. And one of the simplest tasks that people have studied in sensing classical field is DC sensing. And it's the following very simple task. So basically, we were trying to detect either there's a small field, B, that's coming into our sensor, or there's no field. And for now, let's assume that the sensing spin is essentially, that the sensor is essentially a single spin that's being affected by the Hamiltonian determined by the field coming into the sensor. So while I'm writing here as a time-dependent object, for this simplest setting, there's essentially no time dependence. It's either just there's no field coming in, which means the Hamiltonian is just 0, or the Hamiltonian is B. And one of the simplest form of this problem is we wanted to distinguish between these two cases. We wanted to detect either there's a small field of B or there's no field. And this problem has been well studied in the sensing literature, as well as in the quantum computing literature under the scope of Hamiltonian learning. And people have also known for a long time that the optimal time for this task is 1/B. So as B gets smaller and smaller, getting closer and closer to 0, the time it takes gets longer and longer. And it's always just this scaling. It's also known as the Heisenberg limit. And people have designed various protocols that can set the Heisenberg limit. And people have also proven lower bounds that says this Heisenberg limit can never be surpassed. And essentially, this optimality has spawned the entire field of quantum sensing, where people try to build the best sensor for sensing these DC fields.
So, one quick question. Like,
Yeah.
usually, the Heisenberg limit refers to sensing, where you're actually asked not only to tell apart these two cases, but
Right.
also to get this value.
Yes.
But here, is it more like a discrimination problem where you could initially have exponential vanishing later? So
Right. Yeah. So here, this is more like an even simpler form of that. Like, in a way, if you wanted to tell between, or you wanted to estimate some observable or parameters with a small error, in a way, you want to think of it as you're trying to distinguish it either between it's 0 or maybe it's plus epsilon or minus epsilon. And hence, in some case, in that sense, this also captures the phenomenon. So one could think about it as, let's say, I wanted to distinguish between either epsilon or 0, and hence this would be 1/epsilon. Or one could also talk about distinguishing between v of t not equal to 0 with some special number, v0, versus v0 plus minus epsilon. And then in that case, the optimal time would also be 1/epsilon, which kind of matches, and just reduces back here, even though we will be replacing v by epsilon. Hope that clarifies here. So yeah, so here we're considering distinguishing tasks that achieves exponentially small failure probability. But here I'm neglecting the failure probability part. Just assume it's like a constant failure probability. Okay. So just to provide some more intuition behind this task, there have been many optimal protocols that one have developed that can achieve this scaling, this Heisenberg scaling. But there are some that was based on entanglement, but some based on this long coherence time. So one of the simplest protocols looks just like this. So in these two cases, either a field is present or a field is absent, and the flow of time goes to the right. Then at time 0, I would initialize the spin to point at some certain direction. And in the case when field is present, the spin will just rotate according to the field. And roughly around pi/b time, the spin will just be rotated over to the other side when the field is present. And on the other case, when field is absent, it would just maintain the same thing. And now at the very end, when we just measure the spin and see if it's pointing up or pointing down, we will be able to tell between either it's present or absent. So that's like the simplest form, the simplest protocol that can solve this in the optimal form. And over the years, or more recently, people have also been developing Hamiltonian learning algorithms that try to learn many-body Hamiltonians. And in a way, it's all similar to that protocol. I mean, it's not as simple, but in some way, what people try to do is to reduce these many-body Hamiltonians back into this case in order to achieve the optimal scale. But yeah, as we can see, in order to achieve the optimal scaling for this simplest sensing problem, there's no need for having a quantum agent. Just initialize some sensors and then sensing spins and then evolve it and now measure, and that's it. However, we can also ask about the second simplest task, which is known as AC sensing. And in this case, the field is not static anymore. It's not time independent anymore, but it actually fluctuates through time. And actually, a lot of the applications that I mentioned, like detecting gravitational wave to detecting dark matter, all fall under this AC sensing setting instead of the DC sensing case. So in AC sensing setting, the field coming in would always be fluctuating as a cosine wave with some unknown frequency omega that belongs to some range, delta omega. And one could consider applications where the delta omega is very small if we kind of know where the frequency is, or there are also applications where delta omega is extremely large, spans over multiple orders of magnitude, if we really have not much knowledge about where the frequency is. And there's also another parameter phi, which corresponds to the phase that's also unknown to us. But the goal here is similar to the previous one, and is to distinguish between whether there's a field coming in or there's no field. This AC sensing task has also been studied for many decades, and there have been a lot of experimental protocols that people have developed and studied. However, I guess experimentalists don't prove lower bounds, so the optimal time until now is still unknown. So far, even though this is still an extremely simple task, we actually don't know what is the optimal time required for solving this problem, for detecting oscillating field. And similarly, we don't know if the protocols that people are using right now is actually optimal or not. So this is going to be one of the main questions or main target that we'd like to talk about. In particular, do we need a quantum AI agent or just a quantum computer that sit next to our quantum sensors, controlling it coherently in order to achieve the optimal time? Or is it more like the DC sensing case, where we can just do some simple control, classical control, and we can solve it optimally? So again, to build up more intuition for AC sensing, let's look at what happens if you just apply the DC sensing protocol to this setting. Then this setting, when the field is present, there will be an oscillating field. So sometimes it will be a positive field, sometimes it will be negative, which means the spins will be rotating sometimes clockwise and sometimes counterclockwise. And it would just be oscillating over the time. So at time 0, it would be like this. So if we now apply DC sensing protocol, at time 0, it will be like this. And now after some short period of time, over the field when it's going like this, when it's a positive field, then it will be rotated, say, clockwise. But now in the next time slice, because the field is now in the negative, it will be rotating the spins counterclockwise and essentially kill off the signal that we have accumulated back then. And now in the next step, everything just keep repeating. So now the spins, when the field is present, will move a little bit and come back, and then just keep fluctuating around the starting. And as a result, after arbitrary long time, when we just measure the spin, like in the original DC sensing protocol, we will not be able to accurately tell apart these two cases. Because when the field is present, it would just be fluctuating around there, and when the field is absent, it would just be staying. So this just directly applying DC sensing protocol will not solve this problem. However, experimentalists have come up with very nice ideas. And one of the best existing protocol for this task conceptually looks like the following. So basically what one does is after evolving it at that first time up period, let's assume that we know what the frequency omega is in this case. Now what we could do is we can just apply a pi pulse that flips the spin. And now in the next period of time, even though originally it's rotating clockwise, so now in that next time step, it will be rotating counterclockwise because we have flipped it. So after rotating counterclockwise, we will still accumulate some signals. And now we just apply a pi pulse again to rotate it back and just keep repeating this process. So now we evolve further, do a pi pulse, and now the backward evolution, or like kind of the other rotation, we'll still accumulate signals, and we do a pi pulse again. And then finally, at time around pi over b, we will accumulate the signal properly. And when we just measure in the initial basis, we will be able to tell if the field is present or the field is absent.
Sorry, are you assuming we know the omega?
Yes, so in this case, yeah, so in this protocol, we first fix what omega is to apply the pi pulse. But of course, as I stated earlier, we don't know what omega is. So in one of these protocols, what people would have to do is they have to sweep through all the distinct frequencies in order to run this protocol.
Do you know what's B in the amplitude?
Oh, it kind of, so there are protocols that also work when B is unknown. So basically, it's like kind of just try it out. You try it out from.
To describe it is when you know B.
Yes, what I described is when I know B, but there are also protocol, and actually the protocol that we present that I'm going to briefly talk about that we come up with also handles the case when B is unknown. So yeah, so this protocol, also known as CPNG sequence, just apply pi pulses and with the right frequency. And as long as the frequency matches with the underlying unknown frequency, then you will get signal. On the other hand, if the frequency of the pi pulses doesn't align with the frequency of the unknown signals, then one doesn't get signal. So the response function basically looks something like this. And so what people have to do is one will have to sweep through all the distinct frequencies. And one could roughly estimate that the effective number of frequency that one needs to go through scales as the bandwidth divided by the field strength. So if the field is strong, then the number of frequency that we need to go through is smaller. But when the field is weak, the number of frequency that we need to go through will be bigger. And together, one can show that the total sensing time for solving this task of detecting oscillating field scales like the formula shown there, which is 1 over b times delta omega over b. So that's the best existing protocols. There are various variants of this that is much more noise robust, etc. But theoretically or conceptually, this is the best known protocol for doing AC sensing, and that is the scale. Yeah.
So I guess previous question, does this also hold when it's a small oscillating field on top of a large DC background?
Yes, basically you can, there are multiple ways of doing it. Like you can first learn the DC field, and then you can like do a control to like kill off its effect. Like you can go into that rotating basis and so on.
Okay.
There are many ways to handle it. Okay, so this is the best known protocol that people are using, for example, in detecting dark matters, etc. I mean, conceptually, this is purely theoretical. But one can easily ask the question, is this the best known protocol? Is this this protocol doesn't require any quantum agents. Just classically control it, just apply pi pulse in some frequencies, get the data out, and then sweep through things. And then you solve this. But one could ask the question, like, is this the best one could achieve? And what about, like, is this the best one could achieve with classical agents? And is this the best one could achieve with quantum agents? One can ask these two questions. So first, the first result that one of the results that we show in this work is to establish a lower bound for this test. Basically, we can show that whenever we have any classical AI agents that can control these quantum sensors. So for now, the setting is just there's only a single spin sensor, but our result also generalizes when there's multiple spins. But when we have the classical AI agents that control quantum sensors, which is the setting of the protocol that I just gave, one could also prove that there's a lower bound that matches the upper bound that was achieved by that protocol that I just presented. And hence, for classical agents, or classical AI-controlled quantum sensors, or classical computer-controlled quantum sensors, the previous protocol is the best possible. However, it still remains open, or even after establishing this, it still remains unclear. What about quantum agents? Is it possible for a quantum AI agent controlling quantum sensors to achieve a speed up over classical AI agents controlling quantum sensors? And that's what I'm going to talk about for the remaining of my time. Sensing with quantum AI. Or in the paper, or how someone like to call it, he likes to call it quantum computing enhanced sensing. So instead of having just a quantum sensor, we now have a quantum computer that sits on the side that can control it, do some data processing, and try to get some enhancement out of it. So the first theorem that we proved in this paper, quantum computing and sensing, is the following. We showed that for this task, the task of detecting oscillating field, there exists a protocol that utilizes quantum computers sitting next to a quantum sensors and processing data coherently that achieves the following scaling. So there's an additional square root, but that's pretty much the improvement. However, what is also quite interesting is that we just come up with some protocols that I'll talk about, but we can also show that this weirdly looking formula is actually the fundamental limit for detecting oscillating field. We can prove that for any protocol, even the futuristic quantum superintelligence that try to control quantum sensors to detect oscillating field, it cannot do asymptotically better than what we achieved with this. There's a matching lower bound that we call the Grover-Heisenberg limit. It's like a new limit that arises, like emerges on its own when we have unknown frequency. So when not only we're trying to detect the field, there's also these oscillating frequency that's unknown, then suddenly we would have to skip. So together we can take that and plug it back into here. For quantum AI agents to solve this task, the optimal time scales like this. And we can then compare between the two. So at first sight, it looks like just some quadratic speedup because we're just taking a square root in delta omega over 2. However, there's something that we can play with here, which is there are actually two parameters. One is the field strength speed, and the second one is the bandwidth delta omega. And as we can see, like the square root is only applying onto some part of it. And that actually causes some interesting effect to happen in terms of quantum advantage. So suppose we look at the case when the field is strong and the bandwidth is large. So basically both B and delta omega are large. The more precisely, the scaling, so we consider delta omega, the bandwidth, like the frequency range, let's say to span across many orders of magnitude. So we consider 10 to the, say, 5 orders of magnitude of different things. And let's say delta omega is capital N. So capital N is the scaling parameter. And we also assume that the field is quite strong. So it's not a weak field limit, but a strong field limit. And here we consider the field to also be growing with N. So the bandwidth is very large, but also the field is very large, with a scaling of N to the mu. So think of mu as some number between 0 and 1. So when mu is 0, it just means the constant field. But when mu is slightly larger than 0, then it would be a field that is also quite large. And now we can plot these two.
One silly question.
Yeah.
You keep the ceiling bracket everywhere.
Yes.
What is it?
Oh, the ceiling. Oh, yeah. So delta omega is just like the frequency range, and then there's also B, which is the field strength. But because there are two parameters, so for example, maybe B is very, very large, and it's even larger than the bandwidth, or maybe the bandwidth is very small because I don't know what the frequency is. Then in that case, at the end, we always get like in that limit, like let's say delta omega is very small, the B is quite large. Then in that case, that scaling would look like that would be like less than 1. But actually, it should always be 1 because the number of frequency we need to test is always 1. So it's just some technicality. It's not too important. Oh.
So here you look at the case where the bandwidth is very large, but I guess typically you would want to have the bandwidth as small as possible because that sets your spectral resolution. So what kind of application would you want this very large?
Yeah, so like here, the thing we're thinking of here is that there's some unknown oscillating field that's coming in, and we don't know the frequency. Like we really don't know. Like maybe some new physics that we're trying to explore. So we really don't know what the frequency actually is, and hence the bandwidth is very large. Like we need to search through this very large space in order to figure it out. So that's the case. Of course, like in in various settings, we would like to try to focus on a certain small bandwidth, because then we can get much faster sensitivity and so on, or much higher sensitivity and so on. But there are also these applications where there are some new physics we're trying to explore, and hence, or some novel physics we're trying to explore, and hence the band we don't know what the frequency is, and the bandwidth is very large.
Just want to clarify, so
Yeah.
what's in the ceiling function should be a number that's dimensions, so there must be
Yes,
some.
that's right.
Some natural constants.
Oh, actually, we're considering them so that they are dimensions. In a way, both of them are like energy unit. So yeah, so then we can just plug in this scaling, and we'll get some formula that looks like this. I'm considering mu to be less than 1, and hence the ceiling function doesn't affect anyone. So mu is less than 1. And now we just get something like this. And then we can plot what this function looks like. So as we change this mu, we will get different type of speed up. So let's look at a few examples. Let's say mu equal to 0. Then this term just becomes n to the 0.5 square root n versus linear in n. So at mu equal to 0, when the field is constant, not a strong field limit, we just get a quadratic speed up. So that's just a kind of a innocuous quadratic speed up. But now when we look at some slightly larger mu, so say mu equal to 0.2, then we can plug into the formula that I was showing earlier. And now in the quantum case, it's n to the 0.2, and the constant case is n to the 0.3, which is now the cubic speed up. And then we can also look at, say, mu equal to 0.3 and plug it in. And now the speed up becomes a power of 10 type of polynomial speed up. And as mu starts to approach 1/3, this kind of polynomial speed up start to explode. And we can get bigger and bigger polynomial speed up. But at the very end, like when mu equal to 1/3, actually all we get is that in the quantum case, this just becomes constant. So when mu equal to 1/3, it just becomes a constant, and this is still scaling. So now at the very end, it becomes like something like constant versus polynomial speed up. But in the intermediate regimes, and when n is very, very large, then we can get something that's beyond quadratic speed up, like cubic speed up or a large polynomial speed up. And that's when we play with these two parameters. There's actually another way to play it. So instead of considering large strong field setting, but we consider weak field setting, it actually becomes smaller than quadratic speed up. So there's another way that it goes, such that it becomes smaller than quadratic. So kind of like mu becoming, say, the mu becomes negative, and actually it becomes smaller than quadratic. But that's kind of some of the quantum advantages that can arise in this very simple looking task of detecting oscillating fields with a lot of different applications. So for the remainder of time, I would like to just quickly overview what the algorithm looks like and what are the key concepts. I'm just going to show a bunch of slides, but feel free to talk to me if you are interested in the details. So the main conceptual idea that we consider here is that we try to turn the classical field coming into the sensor into what's known into a quantum oracle. So hopefully, for those of you who have taken standard quantum computing courses, there's this discussion about Simon's oracle and quantum oracles that allows one to show all kinds of quantum advantages. Essentially, what we're trying to reproduce that here. But here we just have some classical field coming in, and now the goal is to turn it into some quantum oracle, and then we can apply some quantum algorithms to analyze and learn from the oracle in order to achieve these advantages. So here's the formula for the most general QC enhanced, quantum computing enhanced sensing protocol. Basically, one can think of it as, at the starting point, n is the number of computing qubits that we have, and this one qubit is our sensor, it's our sensing qubit. And this UJ that's shown here corresponds to the quantum circuit or quantum data processing that we apply. And this part corresponds to evolving the sensing qubit under the external classical field. So this is this identity acts on the n quantum computing qubits, and this is just a single qubit unitary that was generated by under the time-dependent signal. So the time-dependent signal comes in, and that affects our sensing qubit. And then we would do some quantum operations on the entire system, n+1 qubits, and then undergo, like the sensor would undergo the external field and repeat. But basically, we can already think of this classical field as some kind of oracle. But it's not a standard oracle that people study in complexity theory. It has two unique features. One is that it only acts on a single qubit, so it's a single qubit oracle. And furthermore, it's time varying. So it's like a time varying single qubit oracle, which is something that is very different from the standard oracle model in quantum complexity theory, because usually in the standard quantum oracle, we have an oracle that acts on many qubits. And furthermore, every time we use it, it's the same thing. It's the same oracle that we access. And then we can design things like Simon's algorithm, Grover search, etc., to get quantum advantages. But here, this is weird. This is like some analog signal coming in. So the idea is that we need to do a digitization. We turn this analog time-varying field signal into some digital quantum operation that looks much more like an oracle problem. And then we can apply existing quantum algorithm to solve the oracle problem. And in this case, the idea that we were, one of the oracle that we can map it into is the standard Grover oracle that looks like this. So basically, when there's no field, the Grover oracle would just be an identity. Every time we query it, nothing happens. But when there is a field of an unknown frequency omega, it will map to a Grover oracle that indexes a certain frequency. So a frequency k that corresponds to a certain frequency bit that we consider. So a lot of our technical contribution in this work is in designing this digitization, try to turn analog time-varying field into a digital quantum operation that is time stationary and acts, but now acts on multiple qubits in order to capture the same information in this time-varying signals. And somehow this is surprisingly complex, so I will not have time to dive into it, but here are the rough steps. So first, we would be using this CPMG pulse sequence that I described earlier, like doing these pi pulses. However, we have to do it in a controlled superposed fashion. So we would be having quantum computer sitting on the side that control this quantum sensing qubit, a quantum sensor. And we'll be applying these control gates in order to do the CPMG sequence in a superposed way. So depending on what is the state on the quantum computer, we will be sensitive to different frequency. But then after doing all of that, it actually creates some badly looking phase structure that is still time dependent. Basically, the phi here corresponds to like what is the time when we enter the field, like what is the underlying phase that was there. So essentially what we need to do is we need to try to digitize it into a form that looks like this. So we want it to have a more sharp, like step function like for the field, and also independent of the underlying phase phi, because phi is changing everything. Like the time varyingness of these oscillating field is essentially in phi. So depending on which time point when we enter, it would actually create a different unitary depending on what this phi is that we enter. So phi changes through time. So in order to do that, we combine some AMO techniques like AC start shift to engineer the Hamiltonian. And then we also utilize some adiabatic quantum computing technique in order to slowly turn things on, in order to kill the phi dependence. There's a way that can once we combine AC start shift and adiabatic path in order to kill the phi dependence. And finally, utilizing quantum signal processing to map it into this like step function like procedure. So essentially, together all of that, we also want to turn the analog time-varying signal into a digitized quantum operation. So it's a very quick thing that I go through, but happy to talk about it in more detail. And after having these digitized quantum Grover oracle, we can just run Grover in order to obtain the final skeleton that we do. And due to time constraint, I just wanted to say that we've also done some noisy physical simulation on NV centers to showcase that actually one can use the NV centers as well as the nearby defects in order to perform this protocol. to do quantum computing enhanced sensing. So finally, to conclude, over the past several years, the community has identified that quantum agents have large advantages in all kinds of quantum problems. However, more recently, we've also seen some results that shows that they're not all powerful and can fail and lack advantages even at some very simple looking tasks. And this raises the question, can we have quantum advantage in more classical problems? And one of the directions that we have been pursuing is in sensing classical fields. And through these study, we have kind of laid out this hierarchy. Basically, we have classical sensors and quantum sensors. And previously, the community has studied a lot of these separations under the ideas of Heisenberg limit and standard quantum limit. And one of the things people want to do is to maximize the quantum Fisher information. However, what we found here in this work is that even for some very simple and foundational sensing tasks, one can also already achieve a further enhancement by considering putting a quantum computer next to a sensor, which we call quantum computing enhanced sensing, which also follows this picture of having quantum agent that can use quantum computers and also use sensors. And there, it seems to be able to host a wide range of new quantum advantages. So I think that's a very exciting that needs to go further in the coming years. That's it. Thank you so much for listening.
Other questions?
So in that plot where you show this oscillation at phase, if you're sensing a noise signal, so there's no phase information, would it also just flatten out?
So could you say again, what do you mean noise signal?
So the AC signal you're considering here has some phase.
Yes.
What if that is noise, so there's no phase information on the signal, just some random fluctuating phase, let's say? What happens to this plot? Do you also just flatten it out?
Oh.
Right, a lot of sensing is in noise spectra, let's say.
I do think, I mean, it depends on the specific setting, but yes, indeed, when every time you come into it and you always have a different phi that might be coming from noise instead of the time variance. Like the reason that here we have this phi come from the fact that we don't know what omega is and some of the, and we also don't know what phi is, and hence there will be some time varyingness. But I think, but yeah, if this phi is just random in the sense that whenever I query the field, it would be some random phase. Then I think the technique that we have will be able to kill that.
Yes,
So,
that would simplify the protocol because you don't have to do the digitization anymore, I guess. But if you just do noise sensing, then would it simplify the protocol? Or because you don't have to get rid of these wiggles anymore? Or
I don't know what do you mean by noise sensing?
well, I mean, if I just want to see if there's a fluctuating source at a certain frequency,
Right.
but I don't need to sense the phase of that noise.
Ah,
Or that it has just random varying phase. I guess very common problem I would think.
right. I think that might not be enough because this plot is not precisely accurate. This plot just corresponds to a single frequency, and we wanted to do a bunch of them in superposition. So I think that's where one complication comes in. My guess is that you're imagining a situation where there's only one of this, and I could do some like learning trick and sensing trick to learn the phi in order to kill it off. But actually, what we need to do is we need to do we need to simultaneously run this in parallel. And I think if one just do that, it collapses it back to classical, so, and hence wouldn't get the advantage that we want to get.
One more question.
A very interesting work is in the end, and I'm a little wondering on like the resource scaling. Like if for every qubit I use for quantum what would be the benefit?
Yeah. So the precise setting, in a way, right. So the number of quantum qubits actually depends only logarithmic on the bandwidth or the number of frequency we need to search. There's not that many quantum computing qubits on me. And also there's only just a single sensing qubit.
But I could put 10 sensing qubits.
That's right.
10 computing qubits.
Yes.
What would be the scaling level?
Yes. Yeah. So there's also like then in that case one can play with how everything would look like. Basically, when one puts n sensing qubit, this would be NV. Like one can just think of as enhancing the strength of V by N times. So this would be NV. This would also be NV. But then of course, then you will have fewer computing qubits to get the speed up, like this type of speed up. So there will be like an intermediate form that goes between these two. So then one can indeed play with how one wants to.
And there's still an advantage if I take the resource usage also into account. Like, because for every computing qubit I can do a sensing qubit. So I feel like is there an advantage if I say like if I put one more computing qubit, I need to add one more sensing qubit for the classic qubit. Just to
I see. You mean like no. I think one more computing qubit, one would need to double the sensing qubit. Yeah, it's logarithmic in the.
I just wanted to, I missed something, I think it was this U parameter, like,
Yes.
somehow for these equations to make dimensional sense, it feels like there's some time that's being set to one. Is that right? Like your kind of N is a dimensionless thing.
Oh no. This capital N here, it will be dimensionful because it will be like there will be some unit one needs to set, and under that unit one.
Are you omega and frequency units?
Yes.
So like, yeah.
Or, I was thinking of them as energy unit, but
Or energy, whatever,
Right.
like, so this is saying V goes as omega to the U.
I
So, like, I
see.
guess I'm. feels
You're
like
saying
there's
like that there's some
scale that you're
unit
implicitly setting to one or something to make it
that is.
sensible, like wondering what that time scale is, like what.
I
Yeah.
see. That is true. Because then in a way N would be unitful and hence now the unit would not match. So one needs to first fix some unit and then talk about this. I think one has to first fix a certain unit that we wanted to talk about and then look at under that unit. Like I think
Is there a natural choice?
I don't think so. I think it would depend on the application, also like the sensor's inherent properties.
Okay, we
Yeah.
can maybe check it
Yeah,
later.
sounds good.
Okay.
All right, I think we're out of time, so let's thank Robert again.
Yes. Which this one? Even further back. Oh. Yeah.
In that case, they use
Yeah, no, it's funny. Yeah.
That's like a read. So in the sense we have a readout. Usually where the estimation of it,
Yeah, this is it's funny, yeah, sure. It's funny. Here.
Yes.
Who are you? Yeah, but using a lot of sensors to try to check. So that's.
This setting much more this setting.
Right. According to that, you still have to. It's usually you general
So them, I think they scan models. And the thing is, one sensor has the same less time on each frequency.
Right.
Compared to a classical sensor. It goes from like 100 years to 3 years.
Yes, that's true. This one is just be the lower bound.
I think it's also.
This one we're proving like the fundamental lower bound for you.
Okay. Very sorry.
I guess have the chance to see you on the mountain.
There's a good chance. I'm just not sure what time of the year it's gonna be busy with kids. But hopefully.
Thank you so much for hosting me here. This time is been a bit brief, but in general,
Yeah, well, let's continue.
sounds good. Yeah,
I really like this project.
Yeah. We're reading something very important examples. I think now to just I'm still.
I haven't read your appendix, so now it's
Grover search, find search authors, the Grover search.
What I haven't just no, and so. Reported back, and so sustainable industry comes errors for me.
Okay, so then afterwards, we'll have to put that run. But it will be, it's better that you revamp